on this journey that we're on to use this thing, which I have to say I'm pretty excited about. So far we've had a look at the machine in general, we've had a look at CAD programs per se, and focused down onto FreeCAD as a way of actually doing this. What I want to do obviously is take this, which I came up with in Tinkercad and printed on the 3D printer, into a metal object that will work under stressful conditions. Because plastic, although it's awesome for prototyping and generating ideas, it won't really perform in the same way in the real world. And what this is a gear reducer. This particular one's 20:1. It's rather chunky because I like it to wear, but I think we can take this down to 60:1, 100:1 in a very compact package. And if you think about that and making it round about the size that'll fit on an EVA stepper motor, then we've got huge potential. So, an exciting project, but it does involve a little bit of work. And one of the bits of work is the prototyping, how you actually get through the design process. Now this was straight from the bat. I just thought this idea, drew it in Tinkercad, immediately printed it, and it worked just fine, which is cool. But when I shrink this down and make it in metal, and this, remember, will take a while and cost me in metal and effort, but will it actually work? And to answer that question, what I really need to do is redraw this. Now, when you're redrawing things, you think, well, why bother? Just print that out. It seems to work, just do it. But it never actually works that way. You very rarely create something that works immediately. The design process is about iteration. You keep on going over and over things, because as you do it, actually you learn something. And as you do it, you think to yourself, well, I wouldn't do that way the next time, I'd do it rather differently. So producing early models give you an opportunity to work out the pros and cons of various choices you've made and whether they will actually work in practice. And before we commit to something permanent, it's much cheaper and easier to work it out this way than it is to work it out by making something on this. This is fast, I mean really fast, but not very durable. This is a little bit slower, but much more durable, and you don't want to commit to this until you've got your design right. And so working through the design is never going to be a matter of one drawing, hey presto. Well, that's not true. I mean, if it's really, really simple, it'll be fine. But if you've got something a bit more complicated, then you are going to be drawing, printing, redrawing, printing until you get what you want. Now, as I said, I want this as something that will go on a stepper motor, maybe. Also, I just so happen to have this. This is all of the aluminium that I've got in thick section. It's a centimetre across, and I can't remember how big that is, but it's 100 that way. So that's my aluminium. That's where I want to make it from. I've also got this, which is a bit of 3mm aluminium sheet. And those two materials are a constraint, along with my design constraint, of the device that I want to make. So, I redrew it. I redrew it actually in 3mm plates, and it's about the right size for a stepper motor, and here's the internals, and this is 120 teeth on that and 122 teeth on that at 0.5 modulus, and so it's round about 70mm across. It fits and it works in the plastic version, and it's pretty cool. Now, it will fit on that. Actually, we've got a couple of plates that'll fit on that, and I get two of them out, so small enough to get out of there. Actually works, and it's just a redesign of this. So we've gone from this to this and that. They're the same thing, they've just been redesigned and redrawn to take into account of some of the considerations I need to have when it comes to actually making something, and whether that thing that I make will actually work. Now you can see that I've actually split it into two parts. These two parts are because I was thinking about cutting the whole thing from 3mm and just bolting it together to make a backplate like that. But then I found I had this, and I thought, well, with this and this, why don't I just make it in one piece? Because this is 10mm deep. I need the pocket here, the bit that's cut out, to be 3mm deep, leaving me in excess of 7mm. I couldn't mill it all down, but then I thought, well, a skater bearing's 7mm, why not just put a skater bearing in there? So, as you can see, as we work this thing out, the design decision for making are changing about how we think we would do it given the light of real materials. So we've come from first prototype where we actually just made the idea. Then we had a consideration about how to make it on this. And then what materials we've got and what size of materials we've got all combine to limit or set the features of your final product. So we've got to go from this now to what's actually going to be the final version, and I'm going to draw that on FreeCAD. So what this video is about, and I'm going to be quite quick on the drawing because we've done the in-depth stuff already, is drawing this up on FreeCAD. Right, let's create a new file. Under that file, let's create a body, which is right there. Under the body, what we're going to do is create a gear. For that, we go to Part Design and Involute Gear. Fill in your gear parameters. I want 120 teeth. I want module 0.5, and I want the pressure angle to be 30. Let's OK that. Click on it so it's highlighted, and then we want to pad it to the thickness, which is going to be 3 millimeters. With body still highlighted, we can hide that pad just by clicking the eye, and now we need to create a sketch. So go to Sketch and create it on the XY plane. We're already in Sketcher and we need to put some circles in there. Click on the circle, tie it to the center. Let's make that 20. This is the circle for the eccentric, and it's fully constrained. Now we need another circle that we're going to move around that's going to engage with the output. So just put that somewhere, make that 14, create the line between the two centers, right click, and then we're going to dimension that line. So click on the dimension, and the distance from center to center needs to be 20 millimeters. So click on that, 20 millimeters, and that will dimension it. Now it's still got 1 degree of freedom, which you can see there, and we need that to be rotated around. And we're going to rotate this through 60 degrees because I'm going to have 6 of those. So click on the dimensions again. On the down arrow, angle constraint. Click on the line that we just drew, and then on the axis. Change that to 60. And there we go. We've got our positioned circle that we're going to need. We need to recreate that. We need to create that at different positions. And one way that I found was relatively easy was to click on the line and delete it. And now we can see that it's under constrained. Also, we've got a constraint here holding these 20 millimeters apart. So click on that and delete it. So now we've got 2 degrees of freedom. What we need to do is lock this down. So we're going to dimension it yet again. Make that 10. And then again. And just click OK on that. So now that's positioned where we want it to be. We need to copy it and move its position. It's circle number 2. So click on circle number 2, keyboard shortcut, and it will create a third circle directly overlaying, and we can see it here. Constraint diameter 14, position 10, 72. Change this position here to -10. And it places it there. Do exactly the same thing, Control-C, Control-V. Move down on your constraints. You can see the circle that we've got. We did that at -10. Change this one to -17.32. Exactly the same thing. Scroll down on the constraints, and this time make both of those minus. And we get 4 of our circles. We now need 2 more. So again, Control-C, Control-V once you've highlighted it. Move down to your constraints, you can see where they are, and this time we want to put it on the axis. We want to put it on this axis here, and it is 17.32 away from it, so double click on it and change that to 0. And double click on that, and remember this time it's 20 because they're 20 from the center to center. Then we can do exactly the same thing, only this time minus 20. And 0. Now we have our sketch. Close it. Let's have a look at the pad again. Highlight the sketch. And this time we're in part design, so we need to extrude it or make a pocket. So click on the pocket icon, and we want this 3mm thick. Now it goes down, it drills down on a pocket, so reverse it so it goes up, click OK, and there we go, we've made our gear. Right, export the STL file and print it, and that's what you get, a genuine part. Now, I'm by no means an expert in FreeCAD. I actually never touched it before, and I'm sure that there are much better ways of doing this, and FreeCAD experts will tell you what a kludge I made of it, and then hopefully promptly tell you the right way to do it. What I'm demonstrating is that basically, with no experience of FreeCAD, I can be up and running in about an hour or two and printing real parts from that 3D design. And that's the whole point. I'm showing you what I did, not the best way of doing it. Because the way to get to do things is actually get your hands dirty, do them. You'll work out ways. As you learn more about it and people help by telling you stuff, then you pick up different ways of doing it that are better, more efficient, whatever. But to do something takes very little time at all. It really takes the willingness to give it a go, and that's the point I'm making. If you give it a go, you'll soon be producing real parts. Don't worry about doing it perfectly, worry about doing it. You'll learn perfectly as you go along. Right, let's do the next bit. Before we continue, I've renamed this. What you do is right click on it, and at the bottom there you've got rename, and you can type in the name. Once we've typed in the name, we can now start our next body. So select the body, click on it, and it will create a whole new body which will become active. When we're in the body, we want to create again involute gear, and that's in part design and down to involute gear. This one I want to be 122, so it's 2 more teeth than the previous one. We want the same module, which is 0.5. And again, we change the pressure angle to 30 because we're going to have this rotate nice and smoothly. When we click here, we've got external gear where we can choose true or false. If it's true, it creates a normal involute gear. If we click false, what we're going to be doing is creating a ring gear. Now we've done that, we can click OK. The next thing we need to do is find the sketch icon and create a sketch on the XY plane. Click OK. And if we leave, swap back to model, there we go. If we leave involute gear as seeable, then we'll be able to draw over it. But remember, highlight sketch so you're drawing on the sketch, and this is like a layers in a paint program. It won't be influenced by what we draw now, but we can draw our sketch. If we click on the rectangle tool, it'll come down there and form a rectangle. Just draw a rectangle, and I want this rectangle to be 75 by 75. So type in 75, hit the tab key, type in 75 again, and hit enter, and we'll get ourselves a rectangle. If we jump to tasks, then we can see that the thing is under constraint, so of course what we need to do is constrain it. Right hand click to get rid of the tool, or click on the other tool and hit the dimensioning tool, because we're going to set dimensions. We set it from the axis here to the edge there, and that will create our dimension for us. Now we did that at 75, so halfway is 37.5. Then we want to do exactly the same thing because we've still got 1 degree of freedom, but this time we've gone from here to here. We go from there to there, so click on the node, pull it, it will do that, and then again 37.5. And now we've got a square actually that is centered on the drawing underneath. Remember, that drawing won't affect it. Right click, and what we want to do now is put a fillet on. So we find the fillet tool, which is right there. Left click on it, then click on one side and the next side, and it will add the fillet automatically for you. In order to dimension the fillet, click on the dimensioning tool, click on the actual fillet you've done, pull it out somewhere, and we can see that we've got the fillet size we can select. Let's select 6, and we've got a fillet there with a radius of 6. We want to repeat that with all of the other fillets. Now these fillets aren't the same, and you can see we've got 3 degrees of freedom. We want to make them the same as this. So click on the fixed fillet and then click on the other fillet, and we're going to use an equals constraint, which is right there. You click constraint equal, then it'll make those 2 fillets exactly the same size, and you can see our degrees of freedom has gone down, and repeat that for the other 2 fillets. Where the fillet begins, we now want to put in a hole, and the hole is so we can put some bolts in. So click on the circle, center it, and we're going to put a 4mm and M4 bolt in there. So just type in 4 and hit enter. And we're doing exactly the same for these other 3. And now we want a hole that the actual axle is going to go through, and what we're going to do here is put in a bearing at 19mm, so make that 19. Now we can close that, and if we undo involute gear, then we can see what our sketch actually looks like. Highlight the sketch, and this time what we're going to do is create a pad. And the pad we want is, in this case, 10mm, because we're going to use a 10mm block of aluminium. And we get our pad with its holes through it. What we need to do now is include the involute gear, because the involute gear is going to create the cutout for the actual gear to fit into. So we click show involute gear, make sure that it's highlighted, and this time click on the pocket icon. When the pocket icon comes up, what we need to do is make it 3.1mm. It just gives it an extra little bit of free play for when we put the actual gear in place. So remember, the pocket drills down, we want it to drill up, so reverse it, click OK. When we spin it round, we can see that it's created an indentation there where our gear will fit. Now we can rename this. Remember, right click on it, click rename, and let's call it backplate. And now we can export it as an STL. Click on File, click on Export, name it, choose STL from the drop-down menu or whatever else you want to do, and click Save. Right, the next bit, let's create a new body, and we'll call it top plate. Why not? Let's rename that. And we're going to create a sketch. But if you remember on backplate, then we had this sketch here for the pocket and here for the pad. This sketch, sketch 1, was that little layout that we did. If we show that sketch, then that sketch essentially we want to repeat. We don't need to draw it all again. So just highlight the sketch and use the shortcut keys to copy, Control-C. Okay. And click somewhere on the plate and Control-V. Now you'll notice, actually, it's under unnamed. It needs to be associated with a body, otherwise it just won't do it. So we can take that, hold it over the name top plate, let go, and it will move sketch 2 into top plate. So now if we hide those, then this sketch has now become part of top plate. It's a whole new sketch. The previous sketch was sketch 1, this is sketch 2, and we can work on this independently. Changing sketch 2 will not affect sketch 1. So if we were to pad sketch 2 in the same way we padded sketch 1, then what we'll get is an extrusion 10mm thick, but you'll notice there's no actual gear on this because we haven't included the involute gear that we did in backplate in top plate, and it saves us a lot of time having to actually redraw things. But we do need to put in an extrusion, a pocket here, to take the actual driven wheel. And the driven wheel is going to be 3 millimeters deep, and it's going to be more or less the same size as the gear. Actually, a little bit smaller will be fine, but more or less the same size as the gear. And it is 60 millimeters across. So if we put a pocket in there of 60 millimeters, we'll get our top plate. In order to do that, we need to create a whole new sketch. Again, on the XY plane, if we close the pad so that we're just looking at the sketch, create a circle, fix it to the center, take it out, and we want a diameter of 60 millimeters. We can then include that by making that a pocket. To make it a pocket, change from sketcher to part design. It's fully constrained. We can close that, and then we can make it a pocket. And again, we want to make the pocket 3.1, just to give it a little bit of clearance. Hit OK. And if we look at top plate now, we can see we've created a pocket, a cutout that will take the drive wheel. Now we've finished that, we can save it and print it. Okay, this is going along rather swimmingly. Now we've got the bottom, we've got the top, and we've got the gear. And the gear goes into the bottom and engages with the teeth. And this centre is driven eccentrically, so it kind of wobbles around there. And as it's wobbling around, it gets driven by one tooth at a time. The distance between this gear and this case is 0.5 millimeter. That's not a lot of distance, but what we need to do is create an eccentric that will do that driving, and of course an output plate. That and a couple of axles, we're done. Okay, we now need to create the eccentric, so let's get a body and let's call that body eccentric. Add a sketch under there in the XY plane, click OK, and we're in the sketch window. Now we're going to be driving this eccentric from only one side, so we need a drive socket for it that won't slip. Something like a hex or a square will do just fine. Let's give it a square. If we give it a square, let's say we'll make that 5 millimeters, hit tab, 5 millimeters, hit enter, and we've got a 5 millimeter square. Now it's unconstrained, and we need to constrain it around that center, because that center is where we're going to place the actual eccentric itself. Remember, this is the eccentric drive. So to do that, obviously we need to dimension it. If we dimension it from this point to this axle, and we make that minus 2.5, then it's nicely centered above here. Now we need to dimension it from this point to this point, but this time we need to make it minus 2.25, because although the eccentric is off center by 1/4 millimeter, that means the throw is twice the distance is off center. So that will give us an eccentric of 0.5 millimeter for a distance away of 1/4 millimeter. Now, of course, what we need is the main eccentric, and that's just a circle at the actual center. So position it at the center, make that 20, because that's the size of the hole that's waiting for it. And there we go. We can close that. We can pad it 3 millimeters. And there's our eccentric. Now we've done that, we need to make the main drive plate. So again, add a body. Let's right click it, rename it, and drive out will do just fine. So now we have a drive out, so let's just get rid of that. And for the drive out, we're going to need 2 sketches. So the first sketch is going to be the size of the main drive, which in this case, of course, was 60 millimeters. So we position it at the center and go to 60 as a diameter. And this equally, we need a square peg in there, because this is the other side of what's driving, only this will be driven out. Let's use a square again. And again, make that 5, hit tab, 5, hit enter. And of course, we want to dimension it. In this case, we're going to dimension it into the center. So we dimension it from there, from that point to that point. And that's going to be minus 2.5. And then from that point to that axis, and that's going to be minus 2.5. And that's the first sketch that we need. So let's close that and add another sketch. On this sketch, what we need are the actual drive holes. Now the drive holes, if you remember from the drive gear, were 20 millimeters away from the center, and the circle that they had was 19 millimeters, 14 millimeters, I apologize. The size of the drive pins is the size of the hole on the gear less the eccentric. So the size of the actual pin that we're going to make is 13.5 and the center is 20 from the center. So we've created our circle that will become our drive pin, and of course it's the same routine. Click dimension, click to that point and dimension it to here. We need that at 20, remember, because we're going to put it on the axis, and then click on that point and this time dimension it to here, and we can make that 0. Now that's in the right place. What we need to do, of course, is swing that round 60 degrees. So click on a line, go to the center of the big circle, and then move it outwards, and you'll see you've got two constraints, length and angle. Now the angle, of course, is going that way. So what we need to do is make this 20, hit tab, and you go to change the angle. We make that 150, which is 90 plus 60. Then hit enter. What that means is the end point of that line needs to be the center of a new circle. Now we dimensioned this circle, if you remember, to the two axes. So if you go to circle and copy it, Control-C, Control-V, we'll get a third circle with associated constraints. What we do is remove those constraints. So just delete them. And then we get an unconstrained circle. Now we want to make sure that we're going to be working on the third element, the circle 2. So hide circle 1. Pull that circle out and then redo circle 1. So now we've got the original circle in its place, and we've got this free floating. What we then want to do is fix this point to this point, and we do that with a coincident constraint. And it's right there. So we click on that, so we get that tool, click on the point there and click on the point at the end of the line there, then it will bring it to exactly the right point. But now, of course, it's fixed at that point, and we don't really want that. So click on the line and delete the line, and you will get two circles. However, it's under constrained by 2 degrees of freedom because we now don't have reference points. We need to give it those reference points, and of course we can do that with the dimension tool. We don't need to change it. We leave it alone where it actually is because we're not moving it. We're just finding out, if you like, what the coordinates are. So once we've found out that coordinate, we then need to find this coordinate, obviously. And we continue with that until we've actually placed the lot. Once we've done that and it's fully constrained, of course, we can close it. Now we've got two sketches we need to tab. They're both showing, but let's undo that one for a second. You can see it's only the pins. If we do that and undo that, it's only the base plate. So sketch 5 is the base plate and sketch 6 is the pins. If we click on sketch 5 and hit pad, then we can pad that to 3 millimeters. Now if we hit sketch 6 and we pad that, we can pad that to 6 millimeters. There we have our drive plate with its drive pins and a central hole. We can now save that and print it. So there it is, printed out and put together. And I've put a dot on this because when I turn the input, of course, the output dot moves a tiny little bit because it's a 60:1 gear ratio, which I thought was really very cool. And I've done this in 3D printing so we can test that the whole idea works. But the point of the video has really not been about the FreeCAD that you need in order to do something like this, but that you don't need much in order to do something like this. I mean, I use very few operations. I don't pretend to be an expert in FreeCAD. What I'm saying is that if you make a start within an hour or two using very simple processes, you can create something that's actually relatively complex. And that's what I believe. I think that 80 to 90% of what you want to do are going to be done with half a dozen tools. when you hit something that you can't do with those tools, well, that's the time to learn that tool so you can then progress, because getting up and running takes no time at all. Getting to be an expert, of course, can take a lifetime. But what you find is that people don't even get up and running because they think they won't be able to do anything. But actually doing stuff is remarkably simple. Now, I'm sure people have better ways of doing this than I did. What I'm showing you are the ways that I discovered to do this in about an hour. So it's all about getting up and trying and doing, and learning is a process that comes with the doing. It's not something that you just pick up by osmosis. Now, a lot of people give you too much information, and that's the problem. It's too much becomes overwhelming because you need surprisingly little to actually create something that's pretty cool. Anyway, I hope you enjoyed the video. Thank you very much for watching, and please do remember to like and subscribe.